Again to our 40th anniversary lecture series. And we are delighted to have in our midst a chemist from Illinois. Cammie Lee Hull received her BA degree in chemistry from Macalester College in 2003, and that's located in St. Paul, Minnesota. She obtained her PhD from the University of Michigan, Go Blue, in 2009 under the influence and mentorship of Professor Melanie S. Sanford. She went on to be an NIH postdoctoral fellow at Stanford University from 2009-2012 in the laboratory of Professor Barry M. Trost. Very nice. Professor Hull joined the faculty of the University of Illinois in the fall of 2012, and she has received many awards over the course of her career, including the Ritt and Mary Cornwall Graduate Fellowship, ACS Division of Organic Chemistry Graduate Fellowship, the Roche Excellence in Chemistry Awards, and NIH Postdoctoral Fellowship, and the NSF Career Award. Very impressive. And she was selected in 2015 by the Chemical Engineering News magazine as one of the talented 12 young scientists and entrepreneurs who are using chemistry to solve global problems. We are delighted to have her here. She had an uneventful trip from Champaign-Urbana, and she has relatives in this area. Is that correct? And we're just delighted to have her here and welcome her and give her your full and undivided attention. I will let her introduce her own talk. Thank you.
Thank you very much for the very kind introduction. It's a lot of fun to come to Andrews University today and share some of the chemistry that I have done in my last few years at the University of Illinois. So, having been to Macalester College, which is the school of about the same size, I know how wonderful it can be to go to a liberal arts university where you get to really know your professors and have enriching experiences with them. So it's great for me to come and share what we do at the University of Illinois, because what I found is that graduate programs are very similar to the experiences you get where you get to really know the professors. And so it's a lot of fun to encourage students to consider types of things like that. And so in my own group, as the ACS Catalysis Award suggested, I'm really focused on green chemistry and the idea of how can we improve organic synthesis to minimize its impact on the environment. So how can we reduce the waste associated with making important organic molecules? And so if you think about it, at this point, learning the tools that you've learned in organic chemistry, you can basically make anything. If we take and combine as many reagents as we want, as much silica gel for those people running column chromatographies today, you can understand this. And lots of solvents, we can make everything. We can make organic materials, we can make the pharmaceuticals you need, we can make the agrochemicals that we spray in the fields. The challenge is, along with all of these very important products, we're also making a lot of waste. And typically what happens with that waste is we burn it. And so which is nice about this, is we actually take this waste, and because it's organic molecules, we can burn it and we turn it into energy, but that still is leading to environmental concerns and health concerns related to that. And so what can we do as organic chemists to help to remediate this problem? And so when thinking about this, I thought about how can we improve our synthetic toolbox to improve the ways that we make molecules. And so one of these things that we can do is we can improve the step economy. So step economy was an idea penned by Paul Wender, who's a professor at Stanford. And his idea was that when synthesizing a target molecule, we want to make this in as few steps as possible, thereby minimizing solvents, purifications, reagents, etc. So if it takes, for example, in 1911, it took 13 steps to convert this cyclic ketone to cyclooctatetraene here. Where in 1948, they were able to develop a nickel catalyst that could do this in a single step. So if you compare this, it took 13 steps and 1 to 2% overall yield. This probably took about 2 months to complete the synthesis, right? That's a lot of time. Whereas using modern chemistry in 1948, they could do that in a single step and 70% yield. So this is a significant advance for synthetic chemistry. The other thing that you want to think about is, like, can we improve atom economy? So the idea behind this is, so this is something coined by Barry Trost, my postdoctoral mentor. And the idea here is that can you minimize how many molecules you throw away at the end of a reaction, and how many atoms you throw away. So for example, If you're thinking about a Wittig reaction, where you take an aldehyde and couple it together with an ylide, you make this alpha-beta unsaturated ester, and you generate triphenylphosphine oxide as your waste product. And so if we think about this, this is actually a pretty heavy byproduct. And looking at this, so if I calculate the molecular weight of each of these compounds, to make a product that weighs 176 molecular weight units, I throw away something that weighs almost 280. Right? This is a very wasteful process in terms of atoms. It's also a wasteful process because this is very hard to separate. And so typically, as organic chemists, we're again running these column chromatographies, this typically streaks through your column. And so not only is this something that you're throwing away at the end of the day, it's also something that makes your purification very challenging. And so instead of using olefination reaction, using modern chemistry, we can think about doing olefin metathesis. Right, so this is a Nobel Prize-winning reaction developed by Professor Bob Grubbs when he was first at Michigan State and now at Caltech. And what he was able to do is develop a ruthenium catalyst that could couple together alkenes to make this new carbon-carbon double bond, and just clipping off the 2 CH2 units as ethene. And so here, to make this same molecule, we now only have to lose 28 molecular weight units rather than the 280 from before. This is still not what we call a perfect atom economy reaction. The ideal reaction is one where you would lose no molecular weights, where all of your starting materials are incorporated into your products. And so that's the ideal goal behind atom economy. So the ideal goal behind step economy is to make everything from starting materials to products in a single step. Atom economy, we want to do that with all of the atoms from the starting materials going into the products. These are obviously ideal reactions, and at this point, synthetic chemists are not even close to be able to do this all in a single step with no waste. But it's a good goal. And so in thinking about this, other things that we want to think about is we want to run our reactions as concentrated as possible because we don't want to waste solvents. Solvents are also waste products we don't necessarily think about. And we want to minimize the purifications required. So we want to do as few column chromatographies as possible, as few recrystallizations. So again, we can just carry everything through and use as little time and as little resources as possible. And so if we can do this, not only will we minimize the impact on the environment of our synthetic chemists, but we also can do things much faster. So economically speaking, this will save a lot of money for the pharmaceutical industry. It will also ideally make medicines and discovering medicines faster, because if you can make the molecules faster, you can screen them faster, and ideally develop new medications quicker. And so in thinking about these overall goals, these big goals for our research group, we then took back and looked at pharmaceutically active molecules. And so here's just an array of some of the top 100 pharmaceuticals, and you'll see that all of these have some sort of carbon-nitrogen bond in them. And actually, if you look at these, 91% of the top 100 pharmaceuticals have some sort of carbon-nitrogen bond. And so in my own research group, what we wanted to do is come up with new ways of making carbon-to-nitrogen bonds selectively in molecules, ideally maximizing our atom economy and maximizing our step economy. And so if we think about how these molecules are often made, so this is Sensipar. This is a drug molecule developed by Amgen, and it treats hypoparathyroidism. And so if we look at the patent routes to this molecule, they first do a condensation reaction to make this alpha-beta unsaturated ester, followed by a condensation reaction, a peptide coupling reaction to make the amide. They do a Raney nickel reduction to make this amide, followed by a LAH reduction to make the amine. So this is neither step economical, nor is this atom economical, because think about all these things we're throwing away along the way. And so you can imagine a much better approach to this would be able to do an anti-Markovnikov selective hydroamination reaction. And this is where you can take a terminal alkene, react it with your amine, and add the NH bond across that alkene selectively to make this product in a single step. This reaction would have 100% atom economy because all of the atoms in both molecules are incorporated into the product. And so this would be ideal in that sense. It would also take these two commercially available starting materials and couple them together, so it would also have excellent step economy for this synthesis. And so although Amgen has a very excellent way of making Sensipar, it's unlikely that they would completely reinvent the wheel based on our chemistry. But you can imagine if you're a medicinal chemist and you're asked to make 100 different variations of Sensipar because you want to make the next Sensipar that's even better, if you can do it in a single step from these two molecules, that's a lot more attractive to you than doing this 4-step synthesis. This might take you an afternoon, where this might take you 2 or 3 days. And so your productivity could be a lot better. And so how do we make amines right now? So just as a review of our organic chemistry, if I asked you to make this terminal amine, we might think about doing an SN2 reaction followed by reduction, or through hydrogenation, or through triphenylphosphine of an azide, or maybe directly SN2 reactions of the amine, but those are kind of challenging to control. We can also think about doing some sort of Mitsunobu reaction or reductive amination. We can do a hydrogenation of a nitro group, which is nice. And so some of these are actually better atom economy than others. Very commonly, actually, people just do this Mitsunobu reaction where they do maybe this anti-Markovnikov selective hydration using a borane, followed by Mitsunobu to form this amine. But again, we think that this would be a much more direct and potentially general approach to doing this. And so what are the challenges? Why is this not already a reaction that people are doing all the time? Well, one thing is that entropically, this is a disfavorable reaction, right? So if we have two molecules coming together to make a single molecule, we're going to have a large negative entropic factor. And so actually, if we heat up our reactions, we make them so they can't occur. And so if we don't have a very efficient catalyst that works at low temperatures, we're not going to get reactivity because once we make it, once the delta G goes positive, we're done, right? And so this is a challenge for us. We also have to think about the fact of catalyst identification. And so if you think back to when you took Organic Chemistry 1, you may have thought about the hydration of olefins or the addition of an alcohol across an alkene. And the way you did this is you reacted with a strong acid, right? So you can protonate the alkene, you make a carbocation, and the alcohol attacks. Why can't we do that with amines? Well, the challenge is if we have the alkene and an amine and we react those with a strong acid, our amine will be protonated first every single time. The pK of an olefin is much, much lower than that of the amine. And so we'll always protonate the amine and we won't see any hydroamination occurring. And so this is not an efficient way of doing this, or a possible way of doing this. So if we can't go back to that, what else can we do? And so I'm a transition metal chemist. These are my favorite things on the periodic table. I love thinking about metals and what they can do, what magic they can do that organic chemists cannot, or just carbon, nitrogen, and oxygen can't do. And so metals are can kind of act like protons. And so if we take an alkene, it can bind to the metal. That can make it electrophilic so that your nucleophilic amine can attack that olefin to form the new carbon-nitrogen bond. And then that hydrogen atom that's now very acidic can now protonate the metal-carbon bond to generate our hydroamination products. And so this is a way that our metal is superior to a proton because it can selectively bind to the alkene rather than to the amine. And so this is a known reaction. So this intramolecular hydroamination reaction was reported in 2008 by John Hartwig. And what he showed is that you can take this bis homoallylic amine with this rhodium catalyst, and you could cyclize it down to make this heterocyclic compound, where this hydrogen atom of the amine was added to the terminal position, and the new CN bond is at the internal position. So this is a Markovnikov selective reaction, where the more nucleophilic piece ends up the more electrophilic carbon. All right, so we know that rhodium can do this reaction from this intramolecular case. But we also have the challenge now, if we have this intermolecular reaction where we have an alkene and an amine coming together, we have to worry about the anti-Markovnikov or the Markovnikov selective process. So does it add to make the terminal CN bond or the internal CN bond? And so with this, if we think about our metal binding to our olefin, we can kind of think of this like a metallocyclopropane, kind of like a bromonium intermediate, where it can now add to either position of that carbon bonds. And so if we think about this, we could have, as our resonance structures of this are potentially in equilibrium, where we have now a carbocation at the internal position or at the terminal position. And hopefully you all remember, this one is much more favored over that one. A primary carbocation is very unstable. And so we would think of the reactivity of this very similar to that bromonium intermediate, where when we form this bromonium and the methanol can attack, we have two different possible choices for that attack. And we always get this product favored where the nucleophile attacks at the more stable carbocation, right? And so we have the same challenge in hydroamination chemistry where it's going to likely attack at the more stable carbocation. And Markovnikov products are typically favored. And so with this, with our olefin bound to our metal complex, the amine is going to attack at this position to form the more substituted the nitrogen carbon bond at the Markovnikov position rather than at the anti-Markovnikov position. And so this is something that we really would like to overcome. We'd like to be able to form either Markovnikov or anti-Markovnikov, but not be limited to one or the other. Okay, and so if we think about this, we go back to this intermolecular reaction, they form the Markovnikov product because that is consistent with it. If we use now specialized substrates where we have now a styrene derivative reacting with amine, we can now have it now has the choice again between the Markovnikov product or the anti-Markovnikov product. And in this case, we actually see a reversal in the regioselectivity because once the rhodium, if you form this rhodium carbon bond at the internal position, you now can form this stabilized complex where that alkene can bind to it. We call this a pi-benzyl intermediate. And so this is now more stable, so we now selectively get this anti-Markovnikov functionalization. And so in thinking about this fourth challenge for us, so we have the regioselectivity issue. We also have the chemoselectivity issue. What products do we get? So ideally, we want the hydroamination products, but we also at times do these oxidative amination products. And what happens is, once we form our metal carbon bond, we have the choice. We can either protonate this or do reductive elimination to form the new carbon-hydrogen bond, or we can do beta hydride elimination, where a hydrogen at the adjacent carbon now forms a new bond with the metal, and we form a new double bond. We form this enamine. And although in those two examples I showed you, I only showed you necessarily the hydroamination product, we also always see competition in forming this oxidative amination product. So we have to figure out ways of controlling so many different factors here in trying to get selective functionalization. And so the approach that my group initially started with was that we started with using alkenes that bear coordinating groups that combine to the metal and help promote reactivity of this alkene. But also, upon the aminometallation or the nucleophilic attack of that amine onto the carbon bond, we can then form this now metallocyclic intermediate. This can't undergo beta hydride elimination because you can't form the necessary conformation to do that. So instead, it should selectively undergo this reductive elimination to form the new carbon-hydrogen bond. Ideally, also, although here I only show you this one metallocycle, ideally, we may be able to control which regiochemistry we get by changing the size of the metallocycle. And so with this, we started with these N-allyl imines. So this is a benzophenone imine. It reacts with morphine. And under discovery conditions, we started seeing hydroamination, which was very exciting for my very young students. And so we indeed did think it was going through this because we didn't see any oxidative amination products. And so we saw no enamine. We only saw the formation of the hydroamination product, which was very exciting. We started with these imines. So we really continued with these imines as we started with these aldimines, which were a little bit easier to synthesize. But also, once you form this, you can either, as shown here, you can undergo reduction to form the secondary amine, or you can hydrolyze it to form the primary amine. So this is a versatile directing group that we can turn into other functionalities if needed. And so what they showed, or what Andrew, Seth, and Anil showed, was if we take these NL imines, or they wanted to see the scope of this reaction. So they started with electron donating groups on this imine, where now you have a resonance structure which makes this nitrogen more anionic, which should make it a better ligand for the metal, and ideally undergo the hydroamination. And indeed, this undergoes the hydroamination in very good yields with these electron donating groups. But what about with other functionalities? And so if we make it more electron donating, so we have this dimethylamine, which makes this resonance structure even more stable and more electron donating, we still see excellent yields. Well, what if we go with electron withdrawing groups? What if we make this as a worse ligand for the metal? If we do this, if we have this ester group here, we're now making this less electron rich of an imine. We still actually see excellent yields. On the top are all in situ identified yields. So we took an NMR and we measured what the yields were. And on the bottom, these are yields of isolated yields after we had to reduce them. And so if we take these imines, groups, electron donating groups are all well tolerated, whether they're resonance withdrawing or inductively withdrawing, we'll still see excellent yields of these products. So for practicality, we form the aldehyde and the amine itself, and so we can't actually isolate these products until we do some sort of chemical functionalization of them. We also wanted to look at what type of nucleophiles work, and so we knew that these secondary cyclic amine nucleophiles worked really nicely for us, which is consistent with the fact if we look at the conformations of these lone pairs are very accessible to do this nucleophilic attack. However, if we make them less nucleophilic, so if we take this diethylamine, we now see almost no reactivity. And so this is a little confusing because this looks very similar to morpholine, right? All we've done is just deleted this oxygen atom, and we see total loss of reactivity. And this is consistent if we think about the conformational analysis of this diethylamine. You could imagine we have these two different conformers. This one is much more favored over that one. And so if we actually think about the Newman projections, everyone's favorite way of thinking about organic molecules, you can think about this lone pair is far more hindered because it has this carbon atom right next to it, rather than the gauche one, where this is much less hindered and more consistent with morpholine. And so just this rotation around this bond, completely we lose reactivity, which is very unfortunate because it limits the reactivity. And so we're trying to figure out ways to overcome this limitation currently. Also, if we react with aniline, so if we have this aromatic substitution there, we also see no reactivity. And this is consistent with the fact it's less nucleophilic because we have now these resonance structures that lone pair is tied up in resonance, and so it's no longer able to react in our reaction. We wanted to think about what happens with these if we add substitution to these allylic positions. And so if we have an arrow group here, which I've indicated is going up, what we imagine is the nucleophile would come from the opposite face, so we'd form this anti-relationship between the arrow ring and the morpholine. And indeed, this was the case. So we saw excellent diastereous activities, even with relatively small groups. And so this was a really nice reaction in terms of that. And so what we think is happening here is we think we're doing a catalytic cycle where we have the imine binding to the rhodium, undergoing this aminometallation reaction. It then can do, as we said, the proton transfer reductive elimination to form our product, and then exchanging off our product ligand for our starting material regenerates the catalytic cycle. And so in thinking about this, if this is really our mechanism, we shouldn't be limited to amine nucleophiles. I love amines. They're in lots of pharmaceutically active molecules, but we don't want to only do hydroamination. And so we also started looking at thiol nucleophiles. And so thiols are also prominent functionalities, and they're relatively hard to install. And what we found is that we can use thiophenol. We can also use this paramethoxythiophenol. But unfortunately, if we use this paranitrophenol, we see, again, total loss in reactivity. And again, this is consistent with, if we think about our resonance structures, that as we add these electron withdrawing groups, we're going to shut down the nucleophilicity and completely stop our reaction. And so I'm going to revisit the molecules I showed you before. If we look at these, they have lots of carbon-nitrogen bonds, but all of these could result from an anti-Markovnikov hydroamination, and all the reactivity I just showed you was from Markovnikov selective hydroamination. So I can't make these right now using the methodology I just showed you. And so we really wanted to address, can we make these types of molecules? And so can we now reverse the regioselectivity and get the harder to form regioisomer rather than this Markovnikov product? And so where we had started was with these allylic directing groups that could form this product. And so if we think about the nucleophile attacking both of these carbon bonds, if we attacked the terminal one, we'd actually form a four-membered ring. And if you guys remember, four-membered rings are very strange relative to five-membered rings. They don't want to form. And so there's no way that we're going to attack that terminal position, because not only is it more electrophilic at the internal position, it also forms a more favored metallocycle. And so our question was, well, what if we now add another methylene spacer in there, make it so that we now have the choice between the potentially could form this five-membered metallocycle, or if it attacks the internal position, a six-membered metallocycle, to potentially, ideally, form this anti-Markovnikov product. And so just to get, five-membered metallocycles are typically more stable than six-membered. Unlike carbocyclic compounds where six-membered rings are less strained, with metals, it typically is the five-membered ring is less strained. But so in looking at this, we actually found that we could make this rhodium complex where we have our amine and our olefin bound, one of our proposed intermediates. And so here's actually an X-ray crystal structure of this. And you can see that we, as I showed you before, we kind of have this metallocycle propane there. And both of these bonds are essentially the same length. So at least in this ground state energy of this X-ray crystal structure, there doesn't seem to be much difference in the electrophilicity. So we can hope that maybe the difference in ring strength can control the regioselectivity. And so if we think about that, if we think about here, so if it attacks the terminal position or the internal position to form the Markovnikov product, we now would actually have this 1,3 diaxial interaction between the phosphine on the rhodium and the position two carbons over with this phenyl ring. Where if we do this five-membered ring, we form this envelope conformation. And that's actually a little bit more flexible, and those arrow rings will potentially, hopefully, not have as much of a bad interaction between the two, and ideally form the anti-Markovnikov product. And what we found, so if we take these now homoallylamines with these diaryl substituents, what we found is we got exclusive selectivity, or essentially exclusive selectivity, for this anti-Markovnikov product, which was really exciting, right? So we're now able to reverse the regioselectivity, of our transformation and get very good yields of this now 1,4-diamine product. But the challenge was, so if we now take and change the substitution here, so not everything is going to have these diaryls there, right? We have to look at the scope of the reaction. So if I make it so it's bigger, so there's methyl group, we now get, so here I say greater than the 20-to-1, we didn't observe the other regioisomer. So this is probably over 100-to-1 regioselectivity. But if I now make them smaller, so if I take my phenyl group and make it a methyl group, we now see 16-to-1. Make 2 butyl groups, we see 5-to-1. And now make one of them a hydrogen atom, we see no selectivity, right? 1.4-to-1, there's a difference of 0.1 kcals per mole. This is not a selective reaction. And so this is a real challenge for us because we don't want to be limited to these diaryl substitutions there. And so again, thinking about our different conformers, so if we have our 6-membered ring, we're hoping that this interaction will control our regioselectivity, but if the R group is a hydrogen atom, that's not a really bad interaction, right? Where the 5-membered ring, again, there's not too much difference there. But maybe if we change our ligand, we might be able to increase the interaction between those. And so here I'm showing you that what we found is we changed from this DPE phos that I was showing you before to now this DPPP. We actually were able to cause this interaction to be bad enough that we could actually restore our regioselectivity. So now, even though it's not quite greater than 20-to-1, we can get 17-to-1 selectivity, even with relatively small groups. We could now have 2 hydrogen atoms there, so no axial or equatorial substituents, and still see 20-to-1 selectivity favoring an anti-Markovnikov product. And so this is really exciting that this ligand is able to control this. We also now hope, although I don't have results in this yet, that we can take that 1-to-1 selectivity and go in the other direction. So can we now make the 1,3 rather than the 1,4-diamine? So I'm going to tell you another story. So that's really our work on hydroamination. Before I told you in our atom economy, in my bad atom economy example, I was talking about the Wittig reaction. And this is a reaction that I've really always been fascinated with because it's a really great transformation where we can take carbonyls and turn them into alkenes. And so, but as I said before, the problem is we're making this really high molecular weight byproduct. And so when thinking about a challenge I wanted to address in my laboratory, I thought about, well, what if we take, and instead of using an ylide, can we take an alkyne using some sort of transition metal catalyst and undergo a reaction between these two to now make this alpha beta unsaturated carbonyl. And so this is going to be more of an inorganic project than an organic project because it's really understanding the fundamental reactivity of these transition metal catalysts. And so again, if we're trying to make alkenes, most of the time we're going to think some sort of olefination reaction. So we can do Wittig olefination, we can do Tebbe couplings, we can do lots of different things, but all of these make these high molecular byproducts. And so the catalytic cycle I wanted to develop to make a 100% atom economy, atom economical Wittig reaction was to take a metal oxo complex, have that react with an alkyne, and do a 2+2 reaction. So this is just a pericyclic reaction to make this metallocyclobutene. You then could take and insert a carbonyl into this metal carbon bond to make this dioxymetallocyclobutene or hexene intermediate, which could undergo a retro-Diels-Alder reaction to regenerate our alpha beta unsaturated carbonyl and regenerate our metal oxo complex. So this would be 100% atom economical. It's redox neutral, so we're not doing any oxidation state changes. And so this would be a really great transformation. The challenge is this step is unprecedented. And so it was known, so these metal oxo complexes have been known in the literature since the 1980s. And what they found is that you have to have very large ligands on them to protect them and to make them stable because they like to polymerize and make paint. So titanium oxos are lovely white solids that crash out of solution. And so they are known, however, if you can trap them with alkynes through this 2+2 reaction. And so the first step of the catalytic cycle was known. It was also known in a single report by Hillhouse that you could take and insert this aldehyde into the alpha beta, the zirconium carbon bond to make this now dioxytitanocyclohexene. And so this was pretty exciting, but he didn't look at the reactivity of this. He just isolated it, reported he made it, but he didn't report anything about this complex. And so the question was, can we now do this retro-Diels-Alder reaction to make these products? And so this is where my student Greg started off in his first year of grad school. And so he actually invented a new route to this molecule because the literature routes were relatively poorly documented and not very pure. It didn't provide pure products. And so what he did is he found that he could do this elimination reaction really nicely and generate this metallocyclobutane really beautifully. And so he was able to demonstrate this on lots of different molecules. He could have 2 aromatic rings. He could have aromatic aliphatic. He could have silyl groups. And all of these were very regioselective. And so this is a really nice precedence that we could potentially do this transformation selectively to form these products. He then looked at doing this insertion reaction, and he found that this worked much better than what Hillhouse reported. You can just add a little bit at room temperature. By the time you walk down to the NMR, you get quantitative conversion to these dioxymetallocyclohexene intermediates. They're beautiful. He was able to get a crystal structure of this. And you can see it almost has a chair conformation, but not quite. So this part is flat, but then it kinks up with this one oxygen. And so the question was, in order to generate our catalytic cycle, will we do the retro-Diels-Alder reaction? And unfortunately, so he takes this, at room temperature it does nothing. He heats it up to 150 degrees. He sees some product, but not a lot. And the thing is that we don't know that this is actually from the retro-Diels-Alder, if this is just decomposition of our metal complex. He then takes and adds a Lewis base, so maybe if we trap this oxo complex, he could promote it, still basically could account for just in decomposition. And then he adds alkyne, so this would really have been a home run for us if we could isolate this along with our product. And again, it didn't quite work as planned. We saw some of this, but not a lot. And so this really wasn't consistent with what we were hoping for our catalytic cycle. And so in thinking about this, we wanted to know, is it just not happening? Is this an impossible reaction? Or is this reversible? And maybe this is a thermodynamic sink. And so in an equilibrium, if this is more thermodynamically stable, it's just always going to lie to the side and not to that side. That doesn't necessarily mean that a catalytic cycle wouldn't be possible. It would just mean that this would be the resting state. And so in order to study this, what Greg did is he took our isolated zirconium complex and he added a different alpha-beta unsaturated alkene. And what he found is that if he heated this at 150 degrees, within 24 hours he reached full equilibrium, where everything was in a 1-to-1 ratio. So we know that this step is possible. We just know that we're thermodynamically biased to form this product. And so what Greg did is he at least showed it stoichiometrically by adding a different alpha-beta unsaturated carbonyl that's going to be a better trap. So here we have a phenyl substituent in this position. Here we have a hydrogen atom. And so this is now a trap for us, and we can start getting very good yields of our alpha-beta unsaturated carbonyls. The challenge here, of course, is that this is not going to work for a catalytic reaction. We could stoichiometrically couple these things together, but we could only ever get one turnover to form our product because this is now going to be an irreversible process. This is now thermodynamically even more stable than our starting complex. And so what we really need to do is now identify a different metal complex that could potentially do this. And what I'll tell you is that we've actually found that titanium can do the same transformation at room temperature. And now we can just trap it with just pyridine or a DMAP derivative rather than with another alpha-beta unsaturated carbonyl. So this is a big improvement for us. Of course, the challenge is we didn't make this through the same synthetic route. We can't get that carbonyl insertion to work. So this is actually something we're really trying to study and improve a little bit more for our future work. Okay, so I'm going to tell one more quick story. And this is a totally different project again. And so I told you about making amines. We're also really interested in making amides. So a lot of those CN bonds are actually amides. So 18% of all reactions run in the pharmaceutical industry are some sort of amidation reaction. So coupling a carboxylic acid derivative and an amine together to make an amide bond. And so we really want to help improve the way that people do that. And one of the really cool reactions that allows for the synthesis of amides is the aminocarbonylation reaction, where you can take an aryl halide, carbon monoxide, and amine and couple them all together using a palladium catalyst to make this amide bond directly. The challenge, of course, is that you have to use between 1 and 200 atmospheres of carbon monoxide, which I'm sure all of you are aware is a very toxic gas that even small amounts will kill you, right? And so this is kind of a scary thing, potentially, especially if you're thinking like 200 atmospheres of pressure of CO, right? And so one of the things that people have really looked into is coming up with CO-releasing molecules. And so in thinking about that, what you can imagine is that you can take and have either a flask where you have on one side some sort of molecule that will undergo a reaction to make CO that then can go into the gaseous phase, transfer over to the other side of the reaction, and undergo your aminocarbonylation reaction. So that's a pretty cool way of doing this. We call that the ex situ approach of CO generation. Or you can have the in situ, where you can have two simultaneous reactions happening, where you have both CO releasing as well as your aminocarbonylation reaction happening in a single flask. And so there's been some really cool work in this. The oldest way of doing this is probably just taking metal carbonyls. So you take moly hexacarbonyl, you add it to your reaction, it releases CO. This sounds great, but these are very volatile. And so you breathe in this metal complex, it goes into your lungs, it releases CO, so you get CO, so carbon monoxide poisoning, and it also leaves the metal in your lungs, so you form nice metallic implants in your lungs. So not necessarily your favorite reaction. If you ever have to use this, use it in a glove box. All right, so don't mess around and breathe that stuff in. So clearly not ideal, but how people have done it for 30 years. Recently, Skydstrup, a Danish chemist, took and developed these organic releasing molecules where you can see here the different functionalities that decarbonylate to form CO, which is actually pretty nice. Especially this one where you use CO2 because it's a very easily accessible gas for us to get. But all of these are about $150. So this one's $150 for 5 grams or 5 millimoles. And so it's actually very expensive. So if you're thinking financially, you're still going to want to use your tank of CO because this is going to be, for most chemists or for most academic chemists, that would be financially, potentially too expensive to really use. And so when we were thinking about this problem, we wanted to look at commodity chemicals that could undergo a reaction that could release CO. And so it's been known since the 1800s that if you take chloroform and you react it with really strong bases, that it undergoes hydrolysis to form carbon monoxide, cesium chloride, and water. Chloroform, although it's not great for you, is something that you use all the time. Every time you take an NMR, you probably are using chloroform as your solvent. Cesium hydroxide is a very inexpensive base that you can use. And so what we actually found is that if we take and just use heterogeneous cesium hydroxide just in the bottom of our flask, so the line in blue here is actually our CO releasing. So within an hour, we've gotten about an 80% yield of carbon monoxide. Other inorganic bases are not quite as good at doing this process. And so what we found is that we could actually use this. We only are using 3 equivalents of chloroform for this transformation to form these amide bonds. And what I want to show you here is that we basically use any amine you want to couple this together, doing using this reaction, where again, we're only using 3 equivalents of chloroform. What's nice too is that we're making so little CO that we can open it up and we're never actually going to achieve toxic levels of carbon monoxide from using our reactions. And so because most of it's absorbed in the reaction, it's actually very safe. We've actually done the math to prove the fact that it's actually safe for us to do and not worry about wearing CO monitors. So it's really nice for that. What's also nice is we're not using any gases at all, and we're using commodity chemicals, so we can just chuck everything together and you can do these reactions. We also can do this so not just with iodobenzene, we can use basically any aerobromide or halide or iodide that you want. And so what Sam did is, so previously in the literature, the largest aminocarbonylation reaction reported was a 5 millimole scale. Well, Sam had to double that, so he was able to do this on a 10 millimole scale and just a heavy walled glass reactor back here. The main thing is you have to do your PV equals nRT and make sure you're not making more gas than the glassware can hold, right? So you don't want to go beyond the pressure of the glassware. But this reaction worked beautifully with essentially no loss in yield. What's also really nice, so if you've taken biochemistry, you've probably talked about labeling reactions where you have deuterium or carbon-13 labels in your molecules. We can now just use C13 chloroform and make C13 labeled carbonyls very easily. Sam did a nice mechanistic experiment to see if the in situ or ex situ setup really mattered. So here you can see everything's all in situ, it's all combined together in one flask. Here you can kind of see a little vial in here where the CO releasing is happening over here and the aminocarbonylation reaction is happening outer vial. And he showed that these are reacting at exactly the same rates. So this reaction, it doesn't matter whether you do in situ or ex situ, it's very fast at CO generation and great at the aminocarbonylation reaction. And the reason I actually ended with this story is this is now a project that is entirely done in my lab by undergrads. Right? So even though we're using something that could be potentially toxic, this carbon monoxide, because we're using it in such small amounts, we're able to now do this and make esters, thioesters, and carbonyls. And so this is actually a project that RU students in my lab worked on last summer, and they will be again this summer. And so I'll end there. I just want to thank these are the graduate students in my lab. So I started 4 years ago, or 3.5 years ago. I have a great set of graduate students in my group that really are exciting to work with and keep me motivated every day. These are some of the undergrads I have in here in my group or have been in my group, but I've just highlighted a couple who are on the papers. And And so some of these, so like Peter Waller was an REU student in my group who's now at Berkeley. Adam Rago is a current undergraduate in my group who's probably going to the University of Chicago for grad school. And Daniel Lee was an REU student last summer in my group who's also applying to grad school. And so a lot of these students, they're not sure what they want to do. And actually, I think it's a great success if you come into my group and you say, at the end of summer, I don't want to be an organic chemist. Like, if you learn from doing a summer of research in a graduate school environment that that's not for you, that's also a success story. Because you don't want to come to a program for graduate school and realize that you hate it and you can't imagine ever wanting to run an organic reaction again. The time to realize that is on an RU program, which actually one of my students last summer realized, and he's now going to become a computational chemist rather than a synthetic organic chemist. I also want to thank these funding agencies for funding. So just a quick couple things about their University of Illinois chemistry department. So we actually have a diverse chemistry department. This is Roger Adams' lab. So he was one of our founding members of our organic area, and the chemistry building is named after him. We also have CLSL, which is the Chemical Life Sciences Laboratory, which is where biochemists and inorganic chemists are primarily housed. This is the Beckman Center, so the Beckman Institute, which is the North Campus, where it's really interactive, where all the labs are merged together and everyone's working on different projects, but in a very collaborative atmosphere. And this is the IGB, the Institute for Genomic Biology, where a lot of my chemical biology colleagues have space as well. We have a lot of Nobel Prize winners who were associated with our chemistry department that we're very proud of, either for short periods of time or for their entire careers they spent there. We also, so one of the things I just want to say is that we have top 10 departments, or top 10 in all areas of chemistry, so not just organic chemistry, but physical chemistry, inorganic chemistry. We have a lot of great things going on. We have fantastic facilities. We also, so in our graduate program, students we try to make them world-class scientists in all different directions. We try to send them to conferences. We try to expose them to lots of different things. And so if you're considering graduate school, please consider coming to our program. The other thing, so I'll just end there. So these are just pictures of our instrumentation. The other thing I just want to really mention is that we do have an RU program. The deadline has not passed yet. It's February 15th. So I highly encourage you, if you have any interest in any area of chemical research, to go on and apply. You just need 2 letters of recommendation. And I'm sure your professors would be happy to provide you with those. And we'd love to expose you to the exciting research that's happening at Illinois. We also do a lot of fun things over the summer. So there's a poster session, but we always do some sort of trip where we go canoeing. We try to really help you to meet the other RU students and have a lot of fun while doing a lot of fun research. And so I will end it there, and I'd be happy to answer any questions. And I talk fast, so I apologize afterwards for that.
Okay, remember, state your name and then your question. Do we have anyone for a question? All right.
I noticed on one of your slides, one of the ways that you can help cut down the steps is to use molecules that get you to the final product.
Right.
But and you've emphasized that the molecules you were using were commercially available.
Right.
How were those commercially available
Made?
made? Like, were they also? Did they have to go through the same process to get to that point? Like,
right. So likely. So the slide you're talking about. Let's go. That is actually something, so in the early steps of syntheses, we don't worry about that as much because you don't necessarily worry about too much on the academic sense where they come from. But I would say that, so this molecule was almost certainly made by just a reductive amination, an asymmetric reductive amination of an imine. So this is probably one-step synthesis to this with a chiral catalyst, where this allyl benzene derivative is probably a one-step route from the aryl halide and a coupling reaction. So it's probably one step to each of those. It is an important thing to think about because a lot of times people will say these are commercially available and it'll be like 1 milligrams for like $1,000, and that clearly, that's kind of cheating when you say that. But these are both relatively easy to make. This one probably is a little bit more expensive, but this is a very common molecule at this point. But that's a very good question.
Oh, go ahead.
Hi, my name is Allie. You mentioned in the olefination section that the transition metal catalysts were remade. And so can those be reused? Do they need to be like purified or something first? Like,
Right. So these molecules are actually, this is about 3 steps from the commercially available starting material. So you take zirconium tetrachloride, you react it with the CP star, or the deprotonated CP star ligand, which is this pentamethyl cyclopentadiene. And then you have to go through several steps to turn it into this hydroxytriflate. From the product of our transformation, which is essentially just like this, it's actually really challenging to go backwards. So what we'd have to do is we'd have to turn it into the dichloride again, and then go through this 3-step process to go into here. So it's not quite something that we can easily recycle. One of the things that, so with our earlier catalyst that I was talking about, the rhodium catalyst, that's very expensive. So to buy 50 grams of our rhodium pre-catalyst is about $1,500. Zirconium is dirt cheap. So although we want it to be catalytic, and it's not atom economical, it's not a great catalyst if it's not catalytic, if we have to use the stoichiometric amount. Economically speaking, it's okay to use it stoichiometrically because it's a very inexpensive metal to use that way, though not easily recyclable, unfortunately.
Question? I'm keeping track, just like Dr. He does.
Maybe I have one question.
Yeah.
On hydro animation, you said for catalyst, the 5-member rings are more stable
Yes.
than organic 6-member ring. My question is, what is the reason behind that one? The second one is, if the catalyst is more stable, does it useful?
Right.
Yeah.
So, so with metals, let's see if this. The 5-member metallocycle is oftentimes more stable than the 6-member metallocycle, primarily because of this, these flagpole interactions between the diaxial substituents in these metallocycles. When you have the 5-member metallocycle, they're more willing to be planar than the 6-membered, and so they're actually minimize the interactions, the negative steric interactions between the ligands and the metallocycle. These are actually, although I'm saying that this is more stable than this one, it actually, neither of these are stable. So we actually have tried to take that, our crystal structure, so we can take this complex that we can isolate, and we can react it with the amine stoichiometrically and try to see these metallocyclic intermediates. And the protonation is so very fast that we cannot observe any of them. So it immediately goes to product. So although one is more stable than the other, it doesn't actually matter in terms of the kinetics, because I think the rate determining step is actually, I think, the aminometallation.
All right.
Yeah.
Thanks.
Oh, okay. Again, state your name. Thank you so much.
Hi, I'm Adriana, and I was just wondering if you've done any reactions that compare like different metals.
Yeah, so we have looked at different metals. And so the ones that we've mostly looked at least for this reaction, we've mostly looked at ones in the same row as rhodium. And what we found is that iridium actually works pretty well as well. Not for this reaction, but it has for a related reaction where we now can add aniline across that double bond. Iridium and rhodium work similarly, but they have the opposite reduced activities, which is pretty exciting because now, depending on the catalyst we choose, we can actually put the aniline at one position or the other. Cobalt, which is actually the one we'd love to use because cobalt is earth abundant, very inexpensive, and doesn't work at all, unfortunately. It tends to do radical chemistry that just is not controllable in our system. And so that's something that we really would like to do. We also, so with the zirconium case, the olefination chemistry, we've done similar studies with titanium because, and what we found is that it does do like the retrocycle addition, but it's so much smaller than zirconium that the carbonyl can't do the insertion reaction. It actually, what it does is it causes it to it causes it to just fall apart, and we do crazy reactions. So we do CH activation, we do CF activation. It does everything but what we want it to do because it's so sterically hindered and so much smaller. But that's, yeah, we definitely are always looking at metals that have similar reactivity patterns as the ones we expect. And so usually those are the ones in the same family because they have similar reactivity trends. Very good question.
So I'm Dave, and I have a question that only a biochemist could probably ask, and that is, clearly, there are individuals working on the theory of catalysts in a catalytic theory using, these transition elements. There are people who are trying to figure out why some. Does Illinois do that kind of thing?
So,
and what is that called exactly? I don't even know what you name it.
So people are definitely looking at like the computational chemistry and trying to model the metals and their reactivities. And so they typically use Gaussian to do that. So oftentimes we'll just call it computational mechanistic or computational physical organic chemistry. So one of my colleagues does do that. She's more on the inorganic side, and she's looking at catalysts that will do hydrogen evolution and water oxidation chemistry. But I actually have a collaborator at Wichita State I went to graduate school with, and she's actually helping us to actually study these complexes and trying to understand why DPE-FOS works so well with one system, but DPPP is essential for the other one, and trying to do those mechanistic studies. So I guess, is that answering your questions?
Yes,
yeah. Most of the time, so theoretical chemists used to do a lot of calculations by hand. And so, but at this point, it is all relying on computers because they can do so much more powerful, so much faster than humans can do.
Well, thank you very much. It was very helpful, and appreciate your time and your travel. And again, thank you so much for being here.
Thank you so much for having me. It's been a lovely day.
A round of applause.